Again, my name is Edward Thomson, and today I'm going to take you through a deep dive into Git. Git, of course, being the very popular Git version control system. How many people are using Git right now at their day job, in an open source project? Okay, let's make that easier. How many people aren't using Git yet? Okay. So I'm going to try to keep this at a level where if you've never used Git before, you can still kind of jump in, but we're not gonna have a getting started with Git session. I'm not gonna tell you how to clone a repository. We're actually gonna crack open a repository and look at what's inside. I think that if you use Git, you'll get a lot of value out of this. I think that if you don't, then we're talking about the internals of a version control system. So there's a lot of great tracks here at the conference, so if this is really boring, feel free to get up and leave. Don't stay bored at this conference. It's a great conference. Real quickly about myself, like Lars said, I'm a software engineer at Microsoft. Who on earth would have thought when I started at Microsoft a couple years ago that I would be talking about Git? Like Lars said, it's been an interesting way to get here. I hope to see you later this week, and I'll tell you all about it at Code. I work on the Visual Studio and Visual Studio Online, sort of the Git integration into that, and I do that. I kind of work at the low level, twiddling bits inside the repository. I work on a project called libgit 2, which is a re-implementation of Git in C. And then, why do we re-implement Git? Git is a really great set of commands, and it does things like malloc, 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 exit. If you want to put that into Visual Studio, you get malloc, 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 don't exit, and all of a sudden Visual Studio is taking up all your RAM and crashing. So libgit 2 is made to not do that, to be a nice library that you can call from any application. And then there's front ends for it for different languages like C#, like Ruby, Java. So you get a nice idiomatic way so that if you want a like Pythonic way to call Git, you can use pygit, and that talks to libgit 2. We're really happy about libgit 2. I've got stickers. If you want to put Git into your application, come get a libgit 2 sticker. I've got some afterwards. And I talk about Git, I write about Git, and I'm branching out into some video training about Git. If you're using Git in Visual Studio, this is a more beginner approach, maybe, and maybe not as nuts and bolts as what you're about to see. But if your team is thinking about ramping up on Git and your Visual Studio users, I'd check it out, gitforvisualstudio.com. You can sign up to be alerted when it's finished. But like I said, we're not talking about how to use Git in Visual Studio. We're going to talk about how Git actually works under the covers. Why should we care about that? I've been doing version control for a long time. Nobody ever wanted to talk to me about the relative merits of Berkeley DB inside Subversion, or how the TFS table layout works. But everybody wants to know how Git works. Why is that? Well, so if you rewind a little bit to how Git was created. Git was created about 10 years ago by a guy named Linus Torvalds. If that name sounds familiar, it's because he wrote the Linux kernel. And he wrote Git to help him write the Linux kernel. He was tired of the version control systems that he had been using. And if you go back to sort of the goals that Linus set when he started creating Git, he wanted it to be fast. He wanted it to be distributed. He wanted it to have some sort of semblance of stability in the face of, or at least he would know if there was corruption. What's not on this list is making it easy to use. And in fact, one of his other points was take any design decision that the CVS project made and do the opposite. And that's, there's some humor in that, but he was really serious when he did that. And for all of its weaknesses, one thing that the CVS team did was that they really cared about an internally consistent and at least understandable system that they were building. Git, on the other hand, it has some strange commands. These last four are my favorite. Checkout does 4 different things depending on what kind of arguments you feed it. And if you get them wrong, well, it can give you some strange error messages. And if you want to try to avoid this and read the man pages, read the documentation, it's not necessarily helpful. I work on Git. Like I deal with the bits in the Git repository on a daily basis. I don't know what the first one means. If you told me that a command was going to forward port local commits to the updated upstream head, I would look at you like you'd grown another head. That makes no sense to me, and I know exactly what that command does. That's the rebase command, by the way. So I think honesty with you is important. I don't want to get up here and lie to you too much, but I'm going to lie to you twice in this presentation, and this is one of them. One of these messages is not a real thing from the Git documentation. The Git documentation is so bad that somebody has actually taken all of the documentation, fed it into a Markov chain, and put a website up that makes fake Git man pages. And you almost can't tell that they're fake. If you haven't seen it, go check it out. If you're curious, it's the reveal all downstream commits below the sent upstream paths. It's the fake one. Yeah, it's kind of hard to tell. The last one's particularly onerous because update remote refs along with associated objects. It should have just been upload your changes, right? So I love Git. Git's a great tool, but it can be hard to use. Fundamentally, when Linus built Git and when Junio Hamano is the current maintainer of Git, great guy, very smart. Junio and Linus are both way smarter than I am, which is one of the problems I have when I use Git, because the Git commands are really just a leaky abstraction on top of the data model. So understanding how the data model works can be really important to using Git. Okay? So how does it work? Let's back up to the very beginning. Git is a distributed version control system. That was one of Linus's goals. What does it mean to be a distributed version control system? Distributed version control systems became popular in the open source world because, if I go into my day job, I'm sitting in an office next to all of my coworkers. We're talking to a central server down the hall, which is good because in centralized version control, you have to be offline. You have to be online, connected to the network, available, talking to the server to do everything. If you want to look at history, you ask the server for the history. The server sends it down. And you, the UI client, you just draw it on the screen for the user. It was a lot easier to write version control clients back in those days. With a distributed version control system, everything is local. All of my commits, all of my history, everything is local. If I want to look at history, I just open up the repository on my hard drive. If I want to check out another branch, all those branches, all the files throughout history are on my local hard drive. I can also commit locally, which is sort of fascinating. That allows me to work independently of one of my coworkers. Because I can commit locally, it actually allows me to do that independently of my coworkers. So I get a nice parallel model for development. So if I'm working and my coworker Alice is working, we can both commit changes to our local repositories. And then we sync those up later down the road, whenever we want, whenever we're connected to the network. We can send those changes and we can merge our changes together. That's actually a really powerful part of Git, is this sort of model. And it's the Git repository, the actual file formats that really enable this to work. So what does the Git repository look like? How does it enable this parallel workflow, this independent distributed workflow? So this is just an example. Let's say I've got, up at the top, this is my repository. I've checked out something from the server, and it's got 3 commits on it. So I've got commit 1, 2, 3 on my server. Alice has done the same thing. On her hard drive, she's got commits 1, commit 2, commit 3. Okay? Now, if we both want to start making changes, I can make a change and commit it to my local repository. It's built on top of those last ones. Alice does the same thing at the same time. Now, when I want Alice's changes, I want to bring those into my repository. So I'll fetch them from the server where she's put them, and I'll bring them into my repository. Unlike a centralized version control system, where at this point the server would figure out our changes and merge them together for us and then give us back some sort of amalgamation of the two that it's figured out. Git doesn't do that, right? I download Alice's commit and it's built on top of commit 3 still. It's not, it has nothing to do with my commit. They're not in any way intertwined until I actually explicitly merge them. And I get a commit that's the combination of those two changes. And this is kind of key to how history is modeled in Git. Let's see if I can figure out how to do this. Excellent. So here I've got that repository that I've been showing you, and I'm going to use, if I just look at the Git log, it just looks like this is what you see if you just run the Git log command, which is how you look at history. This is what you see on GitHub. This is what you see on Visual Studio Online. This is what you see on these websites. And it's just a flat list of commits. And it doesn't really elucidate that sort of flow that I was showing you. So instead, if you use this command, git log --graph --one line, you actually can see how history sort of branches off, and I make my change, Alice makes her change. They both point to that original commit that they both started from. And then they come back together in that merged commit that includes both of our changes. Okay, you can use other tools. There's git k, there's git x, which opened up way behind here, and pardon me. Didn't realize I had audio. And they'll also show you this graph. So it's really just the websites and the default Git log that tries to show you this linear list of history that's helpful. I like looking at the graph. So because I think it really illustrates what Git is actually doing. Okay. There we go. So Git actually, we've seen this graph, we've talked about this graph. Git actually stores its data in this graph. It's called a directed acyclic graph. I failed graph theory, so I'm going to try to walk you through what that means. It's directed. An undirected graph, nodes are just connected to each other. In a directed graph, one node actually points to the next. And so Git actually has direction in its graph. And it's acyclic. If it had a cycle, a node could be pointing back to itself, then you have a cycle from 1 to 2 to 3 back to 1. You can't do that. So these are actually building off each other, pointing to their parents. Commit 2 builds on commit 1. Commit 3 builds on commit 2. You can't have commit 1 building back on the future, which makes sense. Time, we at least perceive it as linear, so this jives with our understanding of time. This is the second lie. I think this is the last lie I'm going to tell you. I hope so. If so, the rest are unintentional. We've talked about these commit IDs as being 1, 2, 3. And when I made a change, I got commit 4. When Alice made a change, she got number 5. How did we know who got 4 and who got 5? Well, in a centralized server, it would just determine who gets the next commit ID. And in Git, it's not so easy because there is no central server. So you can't just do 1, 2, 3, 4, 5. We need a better strategy in Git. We could use a random number. We could use a GUID. What Git actually does is really clever. It actually takes a SHA-1 hash of the contents of the commit, and that becomes the commit ID. SHA-1 is a 160-bit hash, so that's 20 bytes. So when you turn that into a hexadecimal string, so that it's nice and easy to work with, so that you're not talking binary, it's actually 40 characters long. So 40 characters of hexadecimal. They get a little unwieldy. Instead, we usually talk about just the first 7 characters. We talk about just enough to uniquely identify that commit in our history. And that's a little better. We're still talking about A50 AVCF, which is kind of a mouthful, but it's not that much worse. My TFS server has 1 million change sets on it, so it's not that much worse than a 7-digit number, really. What do I mean when I say that we hash the contents of the commit? What does that mean? A commit is a snapshot of the entire repository. If you've worked with Git, a lot of times if you run git show on your commit, or if you upload it to GitHub, you see a diff. So it's very easy to think of Git as storing patches from one revision to another. That's not actually how Git stores its data. Git stores a snapshot of the entire repository at every point in time. And especially if you've got every file and every commit, it sounds like that gets very expensive very quickly. It doesn't. And here's how Git gets around that expense. When Git builds a commit, it builds this snapshot. It points to what it calls tree objects and blob objects. Trees are files, trees are directories, blobs are files. If I have just my first commit in history, I'm adding one file, file1.txt. I have a commit, and it points to a tree. That's my root directory for my repository. Inside that directory, I have just one blob, one file, called file1.txt. And you'll notice, like commits have IDs, the other objects, blobs and trees, also have IDs. So when we build this, when we build our repository, when we build our first commit, we're adding file1.txt. We take file1.txt and we hash it with SHA-1, same mechanism that we use for commits. And we get its ID, and that becomes its blob ID. And then we build a tree that points to that blob by its ID and its file name. And we hash that. That becomes the tree ID. And then we put that into a commit. And we hash it, and that becomes our commit ID. When we add another file, so we're taking snapshots. When we add another file, our next commit, let's say we add file2.txt and commit it. We hash file2.txt and create a blob out of that. File 1 didn't change. Its blob ID stays the same. So we don't have a new object for file1.txt. So ultimately, we're only storing the changes, even though we get a snapshot of the full tree when we actually look at the commit, when we look at the tree. And of course, our tree ID changed because it now lists a second file from before. Okay, let's take a look at that. Let's look at just this second commit, which is 69A46F. See, it is a little unwieldy to talk about them. Pardon me. There we go. So if we look at, this is what you typically work with in a Git repository. This is our working directory, right? I've just got it checked out. I've got a couple of files, file1.txt, file2.txt. I've kept adding a few more. And then there's a .git folder. If you're on Windows, this is hidden by default. It's got the hidden attribute, so you can't see it unless you show hidden files. I always unhide these because I love actually getting inside the Git directory. I mean, maybe don't make changes in there without knowing what you're doing, but let's poke around, right? So inside the .git directory, I have a bunch of other directories. This is actually my repository. This is the database. This is how my repository works. And one of these directories is the objects directory. And inside there, I've got a bunch of 2-character directory names. I said I was looking at object 69 something. So the first 2 characters correspond to the first 2 characters of the object ID that's stored there. So my objects are actually just stored on disk. Object 69A46F is just in a file called objects/69/A846F. We can't really look at that directly. If I just open the file up, it's a binary file. It's actually just a compressed file. So instead, I'm going to use a git command called catfile. Git catfile will actually just extract this file and just dump it to the screen so I can see exactly what Git is storing for a commit. And I only have to give it the first couple characters, just enough of the commit ID, just enough to be able to uniquely find it in the repository. And this is actually our commit. Again, it points to a tree that actually has all the changes. It points to its parent. That's how it builds the directed acyclic graph. A commit stores a pointer to its parent. There's some metadata and then a commit message. Who created the commit and when. If I want to look at the tree that this commit points to, I can use cat file tree, and I'll be really disappointed if I do. It turns out the tree is one of the very few formats in the Git repository that's binary. Just for a little bit of speed up in parsing it, I can use a different command called lstree. And again, I just give it the ID. And really, all it does is store the hierarchy of the file system. I've got two files in here, file1.txt, file2.txt. And I can go back to cat file to look at blobs, since nothing binary about them. And if I run cat file blob, I just get the contents of the file. So there are these very, very simple file formats that are combined to make a very powerful system. Again, if I want to, all these file formats, these commits, these text files, basically, actually build the structure of our repository. If I want to, if I look at my most recent commit, it's a merge commit. It's got two parents. So it actually, when you display the Git graph, it just starts at the tip. Your most recent commit finds the parents and keeps drawing them. That's actually how it draws the graph. Okay. Great. Commits are great, but it turns out that being able to commit in a version control system is not really so helpful unless you can also branch. If you only have one branch, if you will, everything's going into master. And if you're checking in while you're working on a feature and Bob needs to ship some really important bug fix, your feature is getting shipped to production too. And that's not good. So we have branches so that I can work on my feature, Bob can work on his super critical bug fix, and he can ship that branch to production while I still keep working and I don't have to live under the tyranny of Bob's bug fix. Branches in Git are really clever. Branches, their entire goal is to support parallel development. We've seen that Git supports parallel development. And it does that in the repository structure, right? That I can make a change and Alice can make a change independently is parallel development. So Git takes advantage of that in its branching structure. Git branches, they exist at the repository level. So unlike some centralized version control systems like TFS or SVN, where you've got like a trunk folder and then you create a branch next to it, another folder, Git branches exist at the repository level. And they exist just as pointers within this graph that we've been creating. So they're exceptionally lightweight. They're very easy to work with. That encourages you to branch often in Git. In Team Foundation Server, you have to be an administrator to create a branch, which is terrible. But in Git, you can create a branch. It only exists on your local file system. Nobody else has to see it. If you don't want the experiment that you've done in that branch, you can just throw it away. Okay. They're really just a pointer in the graph. So if we extend this repository we've been looking at, when I merged Alice's changes, which were on her branch, into mine, they moved into my branch. Okay. To see just how lightweight they really are, here in my .git folder, there we go. Here in my .git folder, next to the objects directory, which is where all our objects are stored, is a directory called refs. And refs is kind of a terrible name, but there are two directories inside that, heads and tags. Tags are for tags, which makes sense. Heads are for branches, which doesn't. But if you can put the bad name aside, if we go into our heads directory and look at what's inside, we've got a file called Alice and a file called mine. And these actually correspond to the branches in my repository right now. And if I get my trusty Git log back out and I run git log -- graph -- one line -- decorate, and if you get really tired of typing this is my favorite Git log command. This is my favorite way to look at history is -- graph -- one line -- decorate. If you get really tired of typing this, make an alias. I've aliased git lol. This is what a lot of people do. Makes me smile every time I run it. So I can run git lol. And so this is what we saw before, except we're now decorating the branches. So you can see Alice points to that commit. My branch points to that commit. And if we look at these two files that are in this refs heads directory, we can see how that works. The Alice file just contains a commit ID. The mine file also just contains a commit ID. These are really just pointers into the graph. When I create a new commit, that number will advance, so it moves me forward. If I go back into my working directory, and let's edit file3.txt. Let's get excited about file3.txt. Let's change that period into an exclamation point. So when I do that, if we zoom in, it tells us that on the mine branch, we've updated commit number 23F9D06. And if we actually look inside our refs heads mine, it points now to 23F whatever. So it's actually advancing that pointer every time we do a commit. Okay. There's another special sort of meta branch pointer in Git, which is called head. That's what keeps track of what branch you're on. And that's also just a text file inside the Git repository. So if I look at this file, .githhead, it's so important that it doesn't even go into a directory, a subdirectory inside .git. And actually, that's true. This is the only file that has to exist for you to be a Git repository. If Git sees a file called head in all caps, you're a Git repository. If it doesn't, you are not. I don't know what you are. It doesn't matter if you have an objects directory and a refs directory. You can have all that other stuff. If you don't have a head, you are not a Git repository. Head is just also a pointer. And it just encodes the name of the repository, the name of the branch that you're on. In this case, I'm on the mine branch. If I switch branches, I can use the git checkout command to check out Alice's branch, switch to the Alice branch. Now if I look at head, points to Alice. So Git switches branches just by updating that file and then checking out the differences. It's very, very efficient. I'm going to switch back to mine. Okay. What happens if I create a new commit? Let's say advanced VI, I can't even see. I change that exclamation point back to a period. So again, mine, the pointer to my branch, is updated to point to the new commit. Head still stays pointing to mine. So the only time head changes is when you check out a new branch. And if I look at my Git log, you can see that head has advanced forward, mine has advanced forward. Okay. So that's the quickest introduction I can give you to Git branches and how they're stored locally. And branches are great, but branches don't really do anything for you unless you can merge them, right? Otherwise, we're just working in separate repositories, really. And Alice and my changes will never coexist. So that's where merging comes in. We've seen merging. We've actually sort of illustrated merging between Alice and myself already. But we didn't talk about what happens to the branch pointers when we do that. When we want to merge Alice's changes into ours, we actually create a new commit and update the pointer to that. And so git merge is basically a three-way merge algorithm, much like what you're used to seeing. It finds all the files. First it finds the common ancestor. So if I'm merging my branch into, let's go back. If we're merging my branch into Alice's branch, we find our common ancestor. Super easy in Git. In Team Foundation Server and Subversion, you've got to keep track of which branches have been merged when. In Git, you just look in the graph. This information is encoded within the graph. the last point at which these two branches were merged, or the last point, or the point at which they first diverged, is your common ancestor. And you can use this for all three-way merge calculations. So to do a three-way merge, you look at the files that are different in my branch versus the common ancestor, and the files that are different between Alice's branch and the common ancestor. And then you have to auto-merge those. So you look at the lines that are different, and you just kind of go step by step, finding the differences. That gives you a new commit, and we update the pointers to match. Okay? What does that actually look like in the repository? Great. So I'm going to, right now we've already done this merge. I'm going to reset myself to the point at which my branch existed and Alice's branch existed, and we had not yet merged them. Another great thing about Git, I can just run git reset, and that will set my branch pointer back to any point in time. If I run git log, now you can see I don't have Alice's change, right? This only has my change. I've got a nice linear history. I've had the first 3 commits that we had in common, then I've created a new commit on top of that. When I run git merge Alice, I'm prompted for a merge message. I'll write one. Sorry. Accidentally typed the wrong thing. I'm going to create a merge message. And when I do, I get that new updated branch. And again, it creates this nice graphical history for me. Okay. So there's a special kind of merge in Git, and that's called a fast-forward merge. And this is something that can really only exist in a distributed version control system that uses a graph to underlie its data store. What if I hadn't made any changes? So what if I checked out a branch, and Alice had checked out a branch, and she'd made some change on it, right? There'd been some change going into my feature branch. And I wanted to merge these 2 branches. It looks really trivial when you look at it like this, right? There's not a lot to do here. And so what Git does is it just moves the branch pointer forward, right? I don't have to do the 3-way merge algorithm because there's no 3 ways, right? There's a common ancestor and there's my commit. They're the same thing. So instead of trying to do some calculation about which files have changed in which branch, Git knows nothing's changed in our branch. So it can just move those pointers forward. And that's what it does. So if you've ever seen that message, a fast forward merge has occurred. You'll see that a lot when you do a pull. If you have the workflow where you have, let's say, a master branch, is usually your main branch's name. Let's say you have a master branch and you keep that exactly up to date with the server, and you only create feature branches, you only work in feature branches, you never do any work for yourself in master. You'll often want to get yourself up to date with the server. You'll do a pull from your master, from the server's master into your master, and it'll tell you it's done a fast forward merge. That's what it's doing when it does that. Okay, so if I actually go back, if I go back to our common ancestor, this is commit number 3 that we've been looking at, and I want to merge Alice's branch into ours. If I run git merge Alice, it tells us that it did a fast forward. Okay, all it did was update the branch pointers. So now where B3F009 was Alice before, now it points mine to that as well. Okay, it hasn't created a new commit. It hasn't actually created a merge in your graph history, but it's done the same thing effectively in terms of what's in your working directory. It's brought Alice's changes into ours. If you really don't want to do that, you can avoid it. And sometimes you don't, right? Sometimes you actually want to see how changes were made. If we if we reset back to that, you can say -- no FF when you do a merge, and that will force Git to actually create a merge commit. You can see it says merge done by the recursive strategy. If I look at my Git log, it actually does make a new commit for that. Okay. There's some value in being able to see how your commits have been made, how your merges have been made, and the actual practice of what's happened in your repository, as opposed to just using fast forward commits. I would only do this on integrations, personally. If I'm doing a pull, you don't want to create a merge commit every time you do a pull into master, probably. But this can be useful if you're trying to merge a feature branch into master and you've maybe rebased it. That's a scary word for a lot of people, rebase. It shouldn't be. What does rebasing actually do? Well, there's actually a couple forms of rebase. There's rebase interactive, and then there's just regular old rebase. Rebase interactive is a special kind of beast. But regular old rebase is actually really straightforward. Rebase, unfortunately, rebase is one of those commands that I used in the example of bad Git documentation commands, where it forward ports local commits onto, I forget what it, I totally forget. The mechanism behind rebase is actually really simple. Here we've got the same repository we've been looking at, where I have a change, Alice has a change. We could merge these commits, and doing so, we would get that nice, graphical history. But if we didn't want that, if we actually wanted our commits to look more like a centralized version control system, where our commits were in a straight line, that might be easier to follow. It might sort of be easier to understand when you're looking at history. Obviously, in this, 5, 6 commits, everything's easy to follow. But in a real workflow where you've got a lot of people working independently, side by side, your graph can get really gnarly. And so rebasing is a way to keep good hygiene for your graph, if you will. And so what you can do is you can actually take this commit, and instead of this divergence in history, you can just pluck it right there. How does that actually work? What Git does in this case is it looks at the changes between your commit or commits. You can rebase several commits and the common ancestor. And it creates patch files for each one of them. So it creates a patch to get to this commit from the common ancestor. Then it checks out Alice's change and applies that patch file with git apply patch. This is a sort of strange way to do things, but it's actually really effective. And what it does is, creating that patch isolated only the changes that you had made in your branch. And then checking out Alice's branch, you can apply those changes. And if they apply cleanly, great. You've got those changes now on Alice's branch. If they don't, you have conflicts and you have to go resolve them. And resolving rebase conflicts is particularly terrible because, like I said, you can rebase multiple commits at a time. And so you can have to resolve the same conflicts over and over and over again. So rebasing is not without some amount of pain from time to time. Let's take a look at what actually happens. So at this point, I'm still just on the mine branch. And if I want to take my commit, just this one commit that I've made independently of Alice's, and kind of bring it to Alice's on top of Alice's branch, I can run git rebase Alice. And can I do no commit here? I cannot, alas. That's too bad. Let's force a conflict, shall we? Pardon me. So I'm going to add the same file that Alice has added. This is guaranteed to conflict when I try to rebase. If I run git rebase Alice, what it's going to do, it says that Wow, it gave a lot of output. It says that the first thing it says is rewinding head to replay your work on top of it, which is one of those messages in Git where it's like, I don't understand what that means. So what it's actually done there is it's created a patch file of all of the commits in my branch that it wants to apply onto Alice's. And then it's rewound the head, meaning it's checked out Alice's branch. It then tries to apply the first patch it made, which was my first commit, and that succeeded. It had tried to apply the second patch, which we knew would conflict because we created the same file at the same time. And now we're in conflict. Okay. If we actually look, I'm serious. Let's take a look at inside the Git directory. There's this Rebase apply directory. And inside there, there's a bunch of stuff. And one of those, lest you think I'm joking, is a patch file that actually, this is an old school Unix patch file that describes how to get from my first commit to my second commit. And it tries to apply that now on top of what's on Alice's branch. And of course, I can fix up my commits. If I'm old school and Unixy, I just get a file with a bunch of arrows in it, and I pick which one I want. I can, of course, invoke a real three-way merge tool if I am not so Unixy. But, you know, I work at Microsoft. I'm very Unixy. Sorry. Rebase continue, and I did a commit in the middle of my rebase, which puts me in a terrible, terrible state. And instead of talking too much about that, I'm going to reset my way right out of it. Hey, oh my God, I didn't reset my way out of it. OK, I'll rebase abort. Hey, there we go. We'll just hand wave and pretend that didn't happen. I ended up accidentally putting myself in a detached head state, which in like all good Git things is a terrible thing. Actually, you know what? I usually don't dwell too much on detached heads. What does it mean? Has anybody seen this message? You're in a detached head state. Keep your hand up if you knew what it meant. There's a couple of people. All right. So what does it mean to be in a detached head state? Generally speaking, we've looked at this head file before, right? This is the pointer to your current branch. If you detach your head, so to speak, Git. There's a bunch of ways you can do it. The easiest way, the most common way that happens is when you accidentally screw up in the middle of a rebase, because when Git does that rewinding head, it actually detaches your head. Oh my God, I'm sorry. I can't even believe I'm saying these words out loud. They don't even make sense to me. But what it's done is it's actually checked out just a commit. It doesn't check out a branch. It checks out a commit. And that's something you can do in Git. If you just run git checkout with a commit ID, it'll give you this huge warning about how you're in a detached head state. And what actually happens is your head file, instead of containing a branch, it now looks like a normal branch where it points to a commit ID instead. And so the same thing happens if I were to, edit a file and commit it. My head pointer still moves forward, right? I still created a commit on top of the old one. My branch pointer, my head pointer still moves forward, but now it's still just pointing to that next commit, which is really unsatisfying. So I'm not really on a branch. And it's really easy to lose changes this way because there's no branch pointer pointing to it. So if I check out mine, it gives me this big warning that I'm losing my changes because they were made on a detached head. So don't get into a detached head state. If you do, it's easy to get out of without losing your changes. So right now I'm in a detached head. Only head is pointing to my commit. I don't have a branch pointer pointing to it, a real branch pointer. I can totally create an easy branch. Okay. So now I'm recovered from my detached head state. I haven't lost anything. Okay. So that's rebasing. Real quick, we've talked about how the repository works under the hood. Real quickly, let's talk about the working directory. And importantly, the index. The index contains a list of all of your files. And I can use another fun Git built-in. Boy. Pardon me. Let's see how I can get out of this one. There we go. I can use another fun built-in called ls files. And so this is my index. When you run git add, when you run git rm, it manipulates this file. The index is unique to Git, and it's actually one of the most powerful things. This is what actually gets turned into my next commit. So if I edit some file and I run git status, it tells me that this file is now untracked. If I run git ls files -- stage, this is probably not something you want to do on a regular basis. But if you like playing with the index, that's fine. And you can look at, you can see that I've still got file 1, file 2, file 3. If I run git add, it adds file 4.txt to the index. So it actually hashes file 4.txt. So when I run git add, it puts the object into my object database. It hashes it. It goes into .git objects 2.5, 7c, blah, blah, blah. And it puts that in the index. Now when I run git status, it tells me it's about to be committed. So what's actually going on here is when Git shows you status, it's showing you the unstaged changes, which is actually just running the diff between what's in your working directory and what's in your index. So when we created file 4 on disk, it was in our working directory, not in our index. It was an unstaged change. When we add it to the index, it becomes a staged change. And it computes that by calculating the difference between the index and what's in your head. Okay? That's the index in a total nutshell. It turns out Git uses the index for a lot of other things, but like when you merge, all that goes into the index. We're going to gloss over that for now. Sadly, we're running out of time. If there are any questions, I will be hanging around after. I apologize I didn't get to them here. Probably outside because I want to give the next speaker plenty of time to set up. But I hope that by cracking open the Git repository, we've seen kind of what's inside, and it's not such a scary place really. And using the Git commands is really just a veneer over manipulating these objects. So by seeing how some of this works, I hope that you've seen maybe how Git works a little bit better for you. Please do rate this session. If you didn't like it, let me know why. I actually give this talk a lot, so I'd love to know, if you don't like it. But thank you. Thanks for making this your first, session here at GoTo. I hope you have a great rest of the week. So thanks.